Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 3.9. This is on the derivatives of logarithmic and exponential functions. And we're going to learn some new rules for finding derivatives. We're going to be learning some new ways to apply the chain rule. And let's talk a little bit about it here, and then we'll look at some examples. So the first thing they want you to know is that e to the x and natural log of x are actually inverse functions of each other. So if we write e to the natural log of x, that's just going to leave you x, as well as natural log of e to the x will just be equal to x as well, and that's for all values of x. And then they have a couple other properties down here. You can read these, but this one is basically just changing from the logarithmic form to the exponential form there. Remember, the natural log is really just, let me write it down. So the natural log of x is just shorthand writing for log base e of x. So these are exactly the same things. It's just that we use the log base e of x so much that we have shorthanded it out to the natural log of x. All right, and then the last one here, we're going to look at some, if you have an x and another value that's greater than 0, and we take that value greater than 0 raised to the x power, that we can write it in a couple of different ways here using e. Remember, e to the natural log of whatever's in there is just equal to that. So just it's gonna help us doing some derivatives here and there. All right. The derivative of the natural log of x, if you just have the independent variable in there, like x, the derivative of that is just going to be 1 over x. This is for all positive values of x. For negative values of x, we have to put around a absolute value bar around the x in the natural log, because we can't actually take the log of a 0 or a negative number. So this is where x is not equal to 0. So if it's positive, just use this. Negative, remember you're getting the same result here, the 1 over x. The same thing if you have something other than just x in here. So this would be for using the chain rule. So if you have a function inside here, you can take the derivative of that function and put it over the function itself. All right, and here is the derivative of b to the x. So if you have some value greater than 0 and not equal to 1, and I challenge you to figure out why you can't have it equal to 1, but then that to the power of x is just equal to b to the x natural log of b. And here's the general power rule that we've been using before, and this just also allows it in the chain rule, which we set some examples of that in the last section. And here's the derivative for the natural log, or excuse me, not natural log, but the log of some base b of x is equal to 1 over x times the natural log of b, and that's for x greater than 0. And it's the same thing if x is going to be less than 0, but remember, x cannot be equal to 0, because once again, we can't take the natural log or the regular log of 0. Let's see what happens if we try to do it in our computer. Natural log of, in our calculator, 0 is undefined. Why? Because, let's take a quick look at that. If I were to go here and just put in natural log of x, and let's do a standard zoom on that, we'll see it actually comes down, comes up here, and then it goes this way. It's never negative. We don't have any negative x values over here, and we don't have, it's not even equal to 0, because the vertical asymptote is y, x is equal to 0. X is equal to 0. All right. So yeah, it's a lot of stuff, but you know, this is things that we need for our toolbox, and it's things that we need to be able to apply here. So let's take a look at an example. All right, here we have y is equal to the natural log of x plus 1 all over x minus 1. And we know that we can't take negative values. We know that the denominator here can't be equal to 0, and we actually know the numerator here can't be equal to 0 as well, because if it was, then we have the natural log of 0, which we can't have. So just kind of keep these things in mind when we find the derivative, and we'll check that our derivative has those same constraints there. All right, so see if you can go ahead and set this up using one of the rules. See how far you can get, and then we will unpause the video and we'll go through the solution. Okay, so here we're looking over here, we're looking for the natural log of something other than just x, and we have that right here. So if we want to take the derivative of this function, so we want to take y prime in this case. So y prime is going to be equal to, well, the derivative of the inside function. And for now, I'm just going to write the derivative because I don't want to work it out yet because it's going to end up using the quotient rule. So I'll just leave it like this and then substitute it in later. So the derivative of the inside function here, all over the inside function, all over x plus 1 over x minus 1, All right, so this is what I have so far. Remember, if I can easily find the derivative, go ahead and put it in there. But if you can't, it's good to just leave it in the, I still need to find the derivative form. All right. So now, off to the side, I'm going to go ahead and find the derivative of that using the quotient rule. So the quotient rule says we take the bottom times the derivative of the top. The derivative of x plus 1 is just 1. It's 1. Minus the top, which is x plus 1. 1 times the derivative of the bottom. The derivative of the bottom is just going to be 1. All over the bottom squared. All over x minus 1 squared. All right, so I'm going to get an x minus x, which is going to cancel the x out, and I'm going to have a negative 1 minus 1, which is negative 2. So this thing will reduce to negative 2 all over x minus 1 quantity squared. And that's the derivative of this function here. So now let's go ahead and replace that, since we calculated the derivative over x minus 1 squared. And this is all going to be over that. So all over x plus 1. Over x minus 1. And so now we just really have to kind of simplify that and make it work here. All right, so let's do that. So this is going to be equal to negative 2 all over x minus 1 quantity squared. And remember, we can multiply it by the reciprocal of the denominator. So this is going to give us x minus 1 over x plus 1. All right. Now, I have two x minus 1s here, one x minus 1 there, so that'll cancel out with one of those, just leave me one left. And my final answer is going to be negative 2 on the top over, and it's going to be x minus 1 times x plus 1, that's the difference of squares, so x squared minus 1. That's it. That's it. All right. I think in the book, they multiplied the top and the bottom by a negative, so they put it as 2 over 1 minus x squared, but these are exactly the same, and I would take either one. All right, let's take a look at another example here. Okay, here we have the function y is equal to 8 raised to the x power. So go ahead, see if you can identify which theorem formula to use, and then when you're ready, unpause and we will go to the solution. All right, I slipped in a super easy one for you, so hopefully you got this. So what is this in the form? Well, we have a positive number raised to a variable here, and that is going to be this one right here, theorem 3.16. This says if we have a b, that's the base, greater than 0, not equal to 1, then we can take this derivative here. So this is just going to be equal to, so y prime is equal to, so derivative of b to the x is just b to the x, so I'm going to write the same thing down, 8 to the x times the natural log of b. B is 8, so times the natural log of 8. And that's it. You're done. You're done. So this one is much more about knowing where to find the formula than it is to go through all the algebra and get it right. All right, let's take a look at another example here. All right, so here's the next one. We have y is equal to 2 raised to the 3 plus sine of x. Now I'm going to give you a little hint on this one. They didn't actually include here how to handle it when your x is something other than just an x there in the exponential position like they did with the others. So remember, you're going to have to end up applying the chain rule and also multiplying by the inside function as well. So just kind of keep the derivative of the inside function. So keep that in mind when you're doing this one. All right, so go ahead and pause the video, see how far you can get, and then unpause it when you're ready. So with this one, I'm going to use this formula here, but I'm really going to be kind of looking at b to the u because this exponent here is not just an x. That means that when I take the derivative, I also have to take the derivative of u by the chain rule here. So I'm going to have y is equal to, all right, b to the x is just 2 plus sine of x, so keep the whole thing here, times the natural log of b. 2 is b here, so times the natural log of 2. And then we're going to have to also multiply this by the derivative with respect to x of the inside function 3 plus sine of x. And I'm just leaving that there just to show you how the chain rule works. So this is just going to be equal to 2, 3 plus, oops, did I not get the sine x in there? 3 plus the sine of x times natural log of 2. And the derivative of 3 plus sine x is just going to be cosine x. So times, oops, mouse starting up again. Come on, stop it, mouse. Times the cosine of x. And that's it. That's it. That's your final answer. Doesn't really matter which one you put first and last, but that looks good. All right, let's look at one more example and see if I can give you a hard, challenging one to do. All right, so for this last one here, we have y is equal to 1 over log base 4 of x. So before you try this one, I know that we can find the derivative of a log with some base here. And you can use this in order to solve this, but you can also do a nice conversion using the base change formula. So you can try it both ways. I think you get equivalent answers both times, but the second way is a little bit more elegant. So go ahead and pause the video, see if you can figure this out, and then we'll go from unpause when you're ready. All right, so I'm going to go ahead and use the change of base formula here in order to get this into the natural log form. Derivatives, natural log is just a little bit easier, and we'll see how that goes. So this is equal to, I'm not taking the derivative yet, but using the base change formula, remember you can write the log base or some base of x as the log of x over the log of 4. So this is going to be the log of x, or excuse me, natural log of x all over the natural log of 4. So right now I can just replace log base 4 of x with natural log of x over the natural log of 4. That's the base change formula if you want to look that up. And then if you just multiply by the reciprocal of the denominator, it just really flips the denominator. So that's equal to the natural log of 4 all over the natural log of x. So now we can go ahead and find the derivative of that. Now notice that the natural log of 4 is just some value, so it's really a constant, so I can pull that out before I find the derivative. So I'm going to have the natural log of 4 times the derivative with respect to x of 1 over natural log of x. And then there's different ways to do it, but what I would do here is I would say natural log of 4 times, and I'm still going to keep that because I'm going to kind of change this around and write this as the natural log of x quantity squared. Not quantity squared, excuse me. To the negative 1. I was getting ahead of myself here. To the negative 1. So all I'm going to do is bring this up to the top here and call it to the negative 1. So that way I can apply the chain rule, the power rule, general power rule, chain rule, and make it a little bit easier. So this is going to be the natural log of 4 times the derivative of this. So it's the derivative of the outside. So just applying the chain rule, you're going to have negative 1. Pull that out, times natural log of x to the negative 2 power, because we have to subtract 1 from there. And then remember, we also have to multiply that by the derivative of the inside, which is just 1 over x. And cleaning this all up, putting the negative exponent stuff on the bottom, we're going to end up, we have a negative there. And on the top, we're going to have just the natural log of 4. And then on the bottom, we have that x, and we can bring this down there too. So this is going to be x, natural log of x, quantity squared. And I believe that is the correct answer. If you have any questions at all, please let me know. And I hope you all have a great rest of your week. Thanks so much.